All right, so here's a couple of things that we've seen previously. You've seen this in Gen Chem. Here's an example of something like lithium. So if you look at lithium in its neutral state should have three valence electrons. If you look at it on the periodic table, it's got an atomic number of 3, right, which means that it has 3 protons. When it's neutral, it has 3 electrons. And if you look at those shells, right, the first one is at 1s, and then there's the 2s and the 2p. And if you look at those shells for lithium, you put those 3 electrons in, 2 go into the 1s, 1 goes into the 2s. Well, the octet rule says that lithium wants to get to a complete shell, a complete number 1 or 2 shell. If you get rid of 1 electron, as we've done here, we've taken these 3 electrons and we've gotten rid of 1 electron. So now that we have just a 1s shell filled, just the 1 shell filled, now we have an extra stable situation for lithium. So lithium will very easily get rid of 1 electron. Here's fluorine. Fluorine has 7 valence electrons. So fluorine is going to do its best to get to 8 valence electrons. So if you're looking at fluorine, right, when we talk about valence electrons, we're talking about in the outer shell. So in the 2 shell, the outermost shell, in the 2 shell of fluorine, there are 7 electrons. So 7 electrons. We don't care about the 1 shell. It's full. It's pretty stable. That's great. We care about the 2 shell in the case of fluorine. If fluorine were to pick up 1 more electron, it would have a full 2 shell, 8 electrons in its number 2 shell. And that would be very stable. So fluorine would rather have an extra electron and become F-. Lithium lost an electron and became Li+. Fluorine gained an electron and became F-. We get to a structure like this, lithium fluoride, where the lithium has a positive charge because it's got a complete 1 shell. That makes it happy. The fluorine has a negative charge because it's got a complete 2 shell. That makes it happy. This compound, lithium fluoride, would be what we call an ionic compound. Ionic compounds are compounds that rely on electrostatic charges to keep them together. So the positive charge of the lithium and the negative charge of the fluorine are attractive charges, right? Opposites attract. They're like those 2 poles of the magnet, right? When you're a kid, when you're playing with magnets, they stick together, right? That's like the lithium and the fluoride. So these guys are held together really strongly, and therefore it takes a lot of energy to melt them. So we're going to see that ionic compounds generally do not melt very low. They're generally very high melting compounds. And lots of inorganic compounds are ionic compounds. These are the reasons why things like rocks don't melt when it gets hot outside, right? It takes really high temperatures like volcanoes to melt rocks. These guys also tend to conduct electricity when they're dissolved in water, and the reason why is because they're dissociating, and those electrons are free to move around a little bit, so they can conduct electricity. And this is how we typically write them, right? We typically write them with charges, right? So you see this positive and negative. That's a good indicator that this is an ionic compound. We don't use lines to represent ionic compounds. And the reason we don't use them in organic chemistry is because we reserve lines for a different type of bond, for covalent bonds. And we're going to talk about that next. All right, so the easiest way to identify an ionic compound. Well, if you see charges are the number 1 way to identify an ionic compound. If you see a positive or a negative charge, you're looking at an ionic compound. So look for those, right? Those will be a dead giveaway for ionic compounds. Sometimes organic molecules contain... Oh, and another way to identify ionic compound is no carbon, right? If you don't see any carbon, frequently you're talking about ionic compounds. Not always, right? But that's one thing that should be tipping you off that this might be an ionic compound. Sometimes you see organic compounds that have ionic bonds within them. Then you'll see these charges written as well, right? There's a charge written. So this is an ionic compound because it's charged, but it's still a organic compound because it's got carbons and hydrogens in it. We don't draw them bonded with lines, right? That line would be a covalent bond. We said we're going to reserve those lines in organic chemistry for covalent bonds. So don't use the lines to draw ionic bonds. Not going to happen. But the lines do get used to draw covalent bonds. All right, so let's take a look at covalent bonds. Covalent bonds are bonding where instead of having electrostatic charges pulling things together, we're going to use a shared pair of electrons to tie two atoms together. So for organic chemistry, let's look at carbon and hydrogen. And the reason we're going to do that is because this is organic chemistry. We're talking about the chemistry of carbon and hydrogen. And if I look at the electron configurations of carbon and hydrogen, right, here I have carbon. Carbon has 6 total electrons, right? Its 1s shell is filled, right? So this is particularly stable. And then its number 2 shell has 4 electrons in it. 1, 2, 3, 4. So I said that atoms like to have 8 valence electrons, or 8 electrons in their outer shell. That's that octet rule coming into play. So carbon only has 4 electrons in its outer shell, 4 electrons in its number 2 shell. So what it can do is pair up its electrons with hydrogen's electrons. So each hydrogen atom should have 1 electron in its outer shell, the 1s. And it wants to pair up its electron with somebody else's electron to get a complete shell too. So by pairing up its electrons, 1 electron from hydrogen with 1 electron from carbon, each one of those atoms can be happy, right? The hydrogen can be happy because it's got a complete number 1 shell. And the carbon can be happy because it's working its way towards a complete number 2 shell. And so because carbon has 4 valence electrons, it's going to work its way up by bonding with 4 hydrogens to get to 8 electrons in its number 2 shell. So by sharing one of each of those 4 electrons with 1 hydrogen atom, that carbon can complete its valence shell, or complete its octet, by pairing up with 4 different hydrogens. So 1 here, 1 here, 1 here, and 1 here. And those lines, those single lines, represent the shared pair of electrons between the carbon and the hydrogen. So because that electron pair is now shared between the hydrogen and the carbon, it ties those 2 atoms together. It keeps them covalently bonded together. They're permanently linked together, because if they want to separate, they have to, each has to give up that stability of having a complete valence shell. So it takes a lot of energy to break that, right? We're not going to do that. In general, covalent bonds are pretty stable. And the last half of this course is going to be talking about how we go about making and breaking those bonds. But all of this is driven by both carbon's and hydrogen's needs to get a complete valence shell. So each one of them needs to get a complete octet, a complete shell, a complete outer shell. All right, so Lewis structures are going to be the way that we represent this initially. Lewis structures depict all of the valence electrons in a molecule. So remember, valence electrons are outer shell. So if it's something like carbon, right? Here's carbon, right? Remember, carbon had, let's see, carbon had the 1s, the 2s, and the 2p, right? And carbon had, 3 2p shells. Carbon had a complete 1s and then 4 electrons in its number 2 shell. For valence electrons, we don't care about the 1s shell. So you've heard me say valence electrons, and let me define that right now. because I've got the retrieval queue here. Valence electrons simply means the electrons that are in the outer shell, the outermost shell of an atom. So for carbon, right, we just drop anything outside the outermost shell. Because carbon has an incomplete number 2 shell, that means that the number 2 shell is the valence shell for carbon, and we don't care about the number 1 shell. There's those 1s electrons, but they're in the number 1 shell. They're very stable. They're not going to react with anything because there's more electrons outside them in the number 2 shell. So the number 2 shell is what's important for carbon. So Lewis structures are going to be the way that we depict all of the electron activity that's going on in the valence shells for all of the atoms in a given molecule. So in a Lewis structure, the atom, the nucleus, is signified by the element symbol, so C for carbon or H for hydrogen. And each valence electron is represented by a dot. So here's a valence electron, here's a valence electron, here's a valence electron, here's one, here's one, here's one, here's one, here's one, right? 8 valence electrons, in this case, 8 electrons around that carbon. And what the Lewis structure does is the Lewis structure shows us where each one of those electrons are. So in this case, this carbon is sharing an electron with this hydrogen. And that shared pair of electrons between the carbon and the hydrogen makes a covalent bond. So I said that each carbon does that 4 times in order to complete the carbon's valence shell, complete the carbon's octet, I should say. So you put 4 hydrogens around. Each hydrogen shares 2 electrons with the carbon. So therefore the carbon has 8 electrons in its octet, and each hydrogen has 2 electrons in its octet, making it happy because its octet is the 1s shell. So the other way we tend to draw Lewis structures is with a line, right? And the line is just showing the covalent bond in a different way. And you can think of these lines as being 2 electrons, right? And every single line in organic chemistry is representing 2 electrons like you would in a Lewis structure. So a quick way to think about valence electrons, here's the periodic table. I mentioned this on a previous slide, but let's just talk about it real quick. If you're in the first row, you want to have 2 valence electrons. If you're in the second row, right, and if you're hydrogen, you have 1, and if you're helium, you have 2, and that's the neutral configuration. So hydrogen always wants to have another electron. It wants to share an electron to get to 2, so that's why each one of these hydrogens has 2 valence electrons. You're right. If you're in the second row, and this is where we spend most of our time in organic chemistry, you want to get to either 8, like neon, or if you're lithium or beryllium, these guys will try to drop down to helium, right? So they'll try to drop down to 2. So 8 total valence electrons. 1, 2, 3, 4, 5, 6, 7, and 8, right? And as you move across the periodic table, you add an electron to the neutral configuration. So lithium's atomic number is 3, right? And that means there are 3 protons. In neutral lithium, you have 3 electrons. If you drop 1, you get down to that stable helium 2 electron configuration, and you get lithium plus. Beryllium's atomic number is 4. That means in the valence shell, you have 2 electrons, and if you drop 2, you get down to that stable helium configuration. Boron's atomic number is 5, and that means you have 3 valence electrons, right? We're subtracting the 2 electrons from the 1s shell. You have 3 valence electrons in the 2 shell. Carbon has 4 valence electrons in the 2 shell, so that means carbon wants to make 4 bonds to get to a complete octet. Nitrogen has 5 electrons, atomic number is 7, 5 electrons in the valence shell. Nitrogen wants to make 3 bonds typically to get to a complete octet. Oxygen is 6 valence electrons, atomic number of 8. 6 valence electrons, wants to make 2 bonds to get to a complete octet. Fluorine has an atomic number of 7, or atomic number of 9, I should say. 7 valence electrons based on the periodic table. right? And therefore it wants to add an additional electron, make one bond to get to that stable neon configuration. So if you notice, as we worked our way across the periodic table, the column descriptor here, 1, 2, 3, 4, 5, 6, 7, or 8, told us how many valence electrons each one of these atoms had, with the exception of helium, right? Helium is over here on the noble gas side because it doesn't actually, because it does have a complete valence shell, even though it only has 2 electrons, right? And those 2 electrons are its complete 1s shell. But for all the atoms that we're going to be concerned about, typically these guys, right? And also these guys. We might come down and talk about these guys as well in the third row. That column descriptor, 3, 4, 5, 6, 7, 8, that group, right, is going to tell you how many valence electrons you have. And therefore, you take 8 and subtract that to say how many bonds are we generally going to make in order to get to a complete octet.